Hi everyone, welcome back to our walkthroughs. So on the second question on the worksheet, we have a filter design. So suppose that we want to design a biomedical sensor that can detect and output recordings of alpha brainwaves in the frequency range 8 Hz to 12 Hz. Unfortunately, it is also picking up gamma brainwaves in the frequency range 40 Hz to 100 Hz, interfering with our ability to get clean recordings of alpha brainwaves. So we want to create a new design for our sensor that can remove this interference, giving us a clear signal. This question really, from the appearance of it, just sounds like a filter question, right? Because that's what we've been doing in filters. We're just trying to block some part of the signal and receive the other parts so that it satisfies our needs. Now, as always, if you want to take a look at this question, think about it yourself, feel free to pause this video. When you're done, unpause the video, and we're going to take a look at this question together. Okay, so for part A, what kind of filter could you use to remove this interference? So since we want to retain the frequency range from 8 Hz to 12 Hz, and the thing that we actually want to have blocked are gamma brain waves in the frequency range 40 Hz to 100 Hz, which is much higher than 8 Hz to 12 Hz. What you actually want is a low pass filter. So you actually want a low pass filter to actually block out this high frequency. Okay. So for part B, we're assuming that we only have access to resistors and capacitors, and we want to sketch the corresponding filter circuit and write out its transfer function. So we know to build a low pass filter using resistors and capacitors, what we're going to do is that we're going to build an RC circuit. So say this is Vn, this is Vn. We're doing an RC, so R goes first, the resistor goes first. And then we have the capacitor that's connected to ground. And this is our V out. This will then be our low pass filter. If we reverse the order of the capacitor and the resistor, it's going to be a high pass filter. So to write out its transfer function, we know that h of j omega is equal to V out tilde over V in tilde. Okay. So as we know in phasor domain, this circuit is just a voltage divider. And so this is equal to ZC, the impedance of the capacitor, over ZR plus ZC, okay, where ZR is the impedance of the resistor. We know that the impedance of the capacitor, ZC, is 1 over J omega C, and the impedance of a resistor is just R. So this is equal to 1 over J omega C over R plus 1 over J omega C, which is then equal to 1 over J omega RC plus 1. Okay, and so that is our transfer function. For part C, it mentions omega C is equal to 1 over RC. That is the cutoff frequency, which determines the frequency at which our filter starts attenuating the signal. If you don't know where this number is coming from, I suggest that you take a look at the walkthroughs for worksheet 3 and the first question in this worksheet. For this question, should we maximize or minimize omega C to remove as much of the interference as possible? So we know that if we think about the Bode plots, the magnitude plot, if we think about the magnitude plot, as omega increases, the magnitude of the transfer function is going to be, if we're on log scale, it's going to first stay at around 1, and then it's going to drop like a cliff. So to remove as much of the interference as possible, we might want to minimize the cutoff frequency omega C, because that's the point starting at which we're going to be attenuating our signal. So if our cutoff frequency is small enough, it can just attenuate much of the signal. Okay. So we want to minimize omega C for part C. And then for part D, say that we can set our cutoff frequency to 10 Hertz, 20 Hertz, 32 Hertz, 100 Hertz, or 120 Hertz. which is the best cutoff frequency and why? So for this very question, as we explained, we should be minimizing our frequency, our cutoff frequency, so that we can remove as much of the interference as possible. But on the other hand, since the part of the input that we want to retain is within the frequency range 8 hertz to 12 hertz, we really shouldn't be attenuating that part. So the cutoff frequency, a cutoff frequency of 10 hertz would probably be inappropriate. So this is actually kind of self-contradicting. On the one hand, we want to remove as much of the interference as possible, meaning that we want to minimize the cutoff frequency. Whereas on the other hand, our ideal frequency, the frequency which we want to retain, which we want to have the input retain, is within the range of 8 hertz to 12 hertz. So that means we should not be reducing omega C to such a level that these kind of frequencies, they get attenuated as well. This is not something ideal, not something we want to see. And so the best cutoff frequency will then just be 20 hertz. All right, so for part E, assuming that we only have a 3.3 kilo ohm resistor in our workstation, what kind of capacitor value should we use for our filter? So for this question, I think this is extremely important. We actually note that the typical frequencies we'll be using, omega C's, are in the unit, like omegas, not just omega C's, are in a unit of radians per second. Okay, whereas the frequencies that are given to us are in a unit of hertz, which is essentially the same as 1/second. Okay, so there's actually this relationship that you can actually do conversions with between these two. So basically, you have omega C being equal to 2 pi f. Okay, to see that what this is true, we can actually draw out a circle and try to think about if I'm moving around a circle at a certain frequency, how many circles am I able to complete within each second? So if I'm moving around a circle at a frequency of omega C, that means each second we're going to be doing omega C radians. Then that's going to be omega C over 2 pi circles, right? Whereas if we're traversing the circle, if we are circling around the circle at a frequency of f, that means each second we're just going around the circle for f times. Okay, that f might not be an integer, but that doesn't matter. So that is actually equal to f. And so we have our relationship right here. Omega C being equal to 2 pi f. We know that omega C is equal to 1/RC. And so our capacitor will then just be C that is equal to 1/2 pi RF. Okay, if we plug in the values, it's going to be 1/2 pi times 3.3 kilo ohm times the frequency, which is 20 hertz. And our resulting capacitor should be around the range of 2.41 microfarads. All right. Okay, moving on to part F. We want to use a computer to plot the magnitude and phase response of this filter. Obviously, you can just call one of the Python scientific libraries to do the job for you. But this isn't like technically required in 16B, the coding part, nor will it be tested on exams. So we're just gonna go ahead and give you the diagrams. The reason why these problems are here is that we want to give you an intuition of what real Bode plots are like and how Bode plots would change as we do certain modifications to the circuit. First up, we have the magnitude plot. Instead of the typical log-log scale or semi-log scale that we've been typically using since we started learning Bode plots, we're not using any of those. Both of the axes, they're linear. Okay, so on the x-axis, we have the frequency, which is f. We wouldn't say it's omega because it's in the unit of hertz instead of radians per second. Okay, and on y-axis, we have the magnitude of the transfer function h of j omega. Its magnitude. So it starts up at 1. As the frequency increases, it's gonna look something like this. So we notice that input with frequency within a range of 8 hertz to 12 hertz, uh, it isn't really like attenuated. That's good. And the input within the range from 40 hertz to 100 hertz. Obviously, I didn't draw it all the way to 100 hertz because I don't want it. But obviously, you can see from the tendency that's been attenuated by a lot. That actually is something we set out to do. Okay. And then we have the phase plot. Again, we're not going to be doing the usual semi-log scale that we've been doing in the typical bode plots, the straight line approximations that we've been typically doing. Instead, we just have linear axes where the frequency, we use the symbol F and is in the unit of hertz. And the y-axis is just the phase of the transfer function. And as the frequency, it increases 10, 20, 30, 40, 50. It's going to go from 0 all the way to negative pi over 2. And it's going to look something like this. Okay, so for part G, we want to take a look at the magnitude phase plots of the previous part and realize that the performance of our filter is rather poor. Its magnitude at 40 hertz is still around 0.5. This is because the alpha and gamma brainwaves are very close together in terms of frequency, and it takes an entire magnitude for a magnitude of the transfer function to drop by a factor of 10, as we have seen in the Bode plots before in question 1. To combat this, we can cascade two of the low-pass filters from the previous part with the same resistor and capacitor values, with a buffer in between as shown below. Okay, so we want to find the transfer function of this circuit and try to find out what the response looks like. In addition, what's going to happen if we cascade a large number of filters together? Using the same technique that we deployed in question 1, we know that the transfer function is just the product of the two transfer functions corresponding to the two filters involved. Okay, so that's going to be equal to the transfer function of the low pass filter squared. And that's going to be 1 over 1 plus j omega RC squared. All right. To get a sense as to why this is true, we notice that this buffer, if we assume that it's ideal, which we are in 16B, we have the two golden rules. The first golden rule states that there is no current flowing in and out of the input terminals. So that means there's not going to be current flowing between the filters, and that these two filters, they're not going to be interfering with each other. The reason why that's true is that the KCL and KVL equation, since there's no current flowing from or to the buffer, the KCL and KVL equations of the two individual filters, they're just going to be the same. And so they're just operating independent of each other. And we can treat the output of the first filter directly as the input to the second filter. Okay. So yeah, basically, if this is something that we call V out 1, something we call V in 2, by the second golden rule, we know that the voltage at two input terminals are the same, and so V out 1 is equal to V in 2. V out 1, its phasor representation is equal to V in tilde times the transfer function of the first filter, right? That's by definition. And that is also equal to the phasor form of V in 2. And so the phasor representation of V out, the overall V out, would then just be V in 2 tilde times H2 of j omega, which is equal to V in tilde times H1 of j omega times H2 of j omega. And so that means the overall transfer function is then just H1 j omega times H2 of j omega. Okay? So to actually get a sense as to what the response actually looks like. We should recall from the last question, last subpart, that the magnitude plot, we only have uh, one of these filters. It looks something. We're obviously not applying the log-log scale, nor are we applying the semi-log scale. It's all linear. It's gonna look like something like this. Okay, where this is one. We know that as we cascade two of these low-pass filters together, we know that its magnitude is just gonna be the magnitude of the low-pass filter squared. Okay, so at each frequency, we're just taking the value at that point from the first graph, from the first diagram, squaring it, and plot it on a second diagram. And since each of these points, they're either 1 or less than 1, that means when we square it, it's going to be lower than what we had previously, right? So it's going to look steeper a little bit. Now, obviously, when I draw it, it's very hard to tell whether it got steeper, but generally, it might be good to understand since the transfer function, its magnitude, it must be no more than 1. When we square it, it's definitely going to be smaller than the original value. So the same logic applies as we cascade together multiple filters. Since we are just multiplying, we're just taking the power of this transfer function, of the norm, of the magnitude of this transfer function to a very large power, it means that our magnitude plot is just going to be steeper and steeper. In particular, when you have something like 10 filters cascaded all together, it's actually going to look like this. Very different from what we previously had. Okay, so that concludes our walkthrough for part G of the question. Now, let's say that our filter is successful as removing the interference we initially detected. We now notice that there is another source of interference, delta brainwaves, in a frequency range 0.5 Hz to 4 Hz. How can we modify our design to remove both sources of interference and get a clear recording of alpha brainwaves? Suppose you do not have access to an op-amp, but you do have access to an inductor. So the thing that we want to do is that we want to filter out both inputs in the low frequencies and inputs in a high frequency. That is exactly what we get if we use a bandpass filter. Since we don't really have an op-amp, the easiest way to build a bandpass filter would be simply to do an RLC bandpass filter, which looks something like this. So this is our inductor, this is our capacitor, and this is our resistor. Okay. So to find the transfer functions of this new circuit, we just apply the techniques that we learned when we were learning phasors. That is, we can just treat this circuit as a voltage divider, since each of the impedance for each of these components is just a constant. It might be complex, but it's still a constant. So the transfer function, h of j omega, is equal to V out tilde over V in tilde. Since this is merely a voltage divider, this is equal to ZR over ZC plus ZL plus ZR, which is then equal to R over 1 over J omega C plus J omega L plus R. And this is then just equal to, if we multiply both sides by J omega C, to J omega RC over 1 plus J omega RC plus J omega squared LC. So after part I, where would we want to set the cutoff frequencies? Okay, so currently we want to capture the alpha brainwaves running at 8 to 12 hertz. That's something we want to keep. There are two kinds of signals that we want to attenuate. First is the gamma brainwaves from 40 to 100 hertz. That's something we want to get attenuated. And the second type of input that we want to get attenuated is delta brainwaves in a frequency range of 0.5 to 4 hertz. Okay, that I also want to get thrown away. So to actually achieve that purpose, we can just simply set the first cutoff frequency, the lower cutoff frequency, to be between 4 and 8 hertz. We can set the higher cutoff frequency to be between 12 to 40 hertz. To make this filter have a better effect, it might be better if we have the two cutoff frequencies they center at the center of our desired frequency range. So we can pick something like 6 hertz and 14 hertz so that the center at 10 hertz, the center of the desired frequency range that we wanted. Obviously, this is an open-ended question, but and the answer obviously isn't restricted to this one. But generally, we will want to have the two cutoff frequencies, they average the center of our desired frequency for best purpose. Okay, so for part J, how can we calculate the cutoff frequency for our filter in terms of R on C? So we know that the cutoff frequency is the frequency at which the magnitude of the transfer function takes on the value of 1 over root 2. So first off, we should be copying over the transfer function. This is equal to j omega RC over 1 plus j omega RC plus j omega squared LC. This is j squared is equal to negative 1. We know this is equal to j omega RC over 1 minus omega squared LC plus j times omega RC. Okay, so the cutoff frequency is the frequency at which the magnitude of the transfer function takes on the value of 1 over root 2, and this is, as we know, the quotient, the magnitude of a quotient is just the quotient of the magnitudes, and that is just going to be equal to the magnitude of j omega RC plus the magnitude of 1 minus omega squared LC plus j omega RC. Okay, and that's just going to be equal to omega RC over 1 minus root of 1 minus omega squared LC squared plus omega RC squared. If we take the square of both sides, we see that this is equivalent to saying that 1/2 is equal to omega squared R omega RC squared over 1 minus omega squared LC squared plus omega RC squared. And so this is equivalent to saying 1 minus omega squared LC squared is equal to omega RC squared. Now, by taking the square root of both sides, we see that 1 minus omega squared LC is equal to plus or minus, because this term can possibly be negative, in fact, is equal to plus or minus omega RC. Okay, and so one of the equations is going to be LC omega squared. It's going to be LC omega squared plus or minus omega, okay, RC omega minus 1 equal to 0. So for each of these equations, for the first equation, LC omega squared plus RC omega minus 1 equals 0. We solve it using the quadratic formula to get omega being equal to negative RC plus or minus RC squared plus 4LC over 2LC. Okay, so obviously, since this term is negative, we can only take the positive term because the frequency can't be negative. And so the only sensible frequency, cutoff frequency that we're going to take will then just be omega being equal to negative RC plus root RC squared plus 4LC over 2LC. Okay, for the other equation, we have LC omega squared minus RC omega minus 1 being equal to 0. So by using the quadratic formula, we see that the two corresponding omegas is just going to be RC plus or minus root RC squared plus 4LC over 2LC. Again, since the thing within the square root is greater than RC squared, we know that the only positive frequency will then just be RC plus root RC squared plus 4LC over 2LC. So the two cutoff frequencies that we eventually end up finding, because we can't really take negative frequencies. So the two cutoff frequencies that we end up getting, because we can't really take negative frequencies, will then just be omega being equal to plus or minus RC plus root RC squared plus 4LC over 2LC. So now, after part K, we want to pick values of R, L, and C so that we can set our cutoff frequency to those picked in part I. And suppose that we have a 500 ohm resistor. What value should we be picking for our capacitor and inductor? So you should first be copying over the two cutoff frequencies that we obtained in the form of this, plus or minus RC plus the root of RC squared plus 4LC. Okay. So let's say we want to have our low cutoff frequency to be at 6 Hz, and that we want to have our high cutoff frequency to be at 14 Hz. If you pick some other frequencies, that's probably also fine, but the effect of this filter, it's probably not going to be as effective. So again, we should be noting that in this question, the omega are in the unit of radians per second. As I derived earlier in this question, we know that omega is equal to 2 pi f. Okay. So the first thing that we notice here is that the difference between the two omegas, the two cutoff frequencies, is equal to R over L. Okay, because we can just get rid of the square root term. That's really convenient. And we know our R, right? On the other hand, we know that delta omega is equal to 2 pi delta f, because this relationship is linear. Okay, so we know that L must just be R over 2 pi delta f. It's just going to be 500 over 16 pi, since the delta f is 8 Hertz. So the resulting inductor, must be 9.95 henries. Okay. We still need to find the value for our capacitor. So to do that, we just add together the two cutoff frequencies. This is equal to root RC squared plus 4LC over LC. Okay, so this is like the RC terms in the front, they just cancel out. And again, we note that this is equal to 2 pi times F1 plus F2, because this relationship is linear. So for the sake of simplicity, we can just divide both sides of the fraction by C to get something like root R squared plus 4L over C over L. Okay, so we know the value of L, we just need to find the value of C. So we know that R squared plus 4L over C, if we move L to the other side and square both sides of the equation, we see this is equal to 2 pi F1 plus F2 L squared. So starting from there, we see that L over C is equal to pi F1 plus F2, which is 20 in this case, L squared. Also, we notice that pi L is just 500 over 16 from this equation. So these two actually combine to 500 over 16. So it's not that disgusting. Minus R squared over 4. Okay, minus R squared over 4. Should probably be writing it in a lovely color. Minus R squared over 4. We know that R is actually 500. Okay, and so if we plug in all the values, we see that C is actually equal to 30.3 microfarads. Okay. And so we have our values for our inductor and for our capacitor. Okay, now off to part L. We want to plot the frequency response of the filter designed above using the resistor, the capacitor, and inductor values picked in the previous part. Uh, Again, for the sake of simplicity, I'm just going to go ahead and give you the plot of this bandpass filter transfer function. We know it's just going to be equal to omega RC over root 1 minus omega squared LC squared plus omega RC squared. So the magnitude plot, again, we're not going to be using a log scale or a semi-log scale. Everything, the axes are just going to be linear. Okay. So we have a magnitude plot. We have the omega, and where you have the magnitude of the transfer function. So it sort of maxes out at the center frequency, which is like 10 hertz, with two cutoff frequencies, one being 6 hertz and the other being 14 hertz. And so the alpha brain waves that we want to capture, that we want to keep, is between 8 and 12. Looks good. And from 40 onwards, looks also good enough. And for 0.5 to 4, it's going to look like this. Okay. That is sort of the idea. This is just a sketch. So we should notice that for this magnitude plot, around the center frequency, that is between the cutoff frequencies, since this is a bandpass filter, the magnitude of the transfer function is close to 1, meaning that those signals, those parts of the signals, they're preserved. Okay. So in part M, we again notice that while the filter is attenuating the necessary frequencies, it isn't doing that good of a job. We want to try plotting the responses if we have multiple filters cascaded with the buffers similar to part G. So using a similar logic as we did in part G, we know that if we have n such n-has filters cascaded each other with buffers in between adjacent filters, then the overall transfer function h of j omega is just going to be equal to the transfer function of each of the bandpass filters to the nth power. Okay, and since the magnitude of product is just the product of the magnitudes, we see that the magnitude of the transfer function is going to be equal to the magnitude of the individual bandpass filters to the n. Okay, and we notice that if you look at the magnitude plot on the top, this diagram, we see that each of the magnitudes at every single frequency is not going to be greater than 1. Okay, so the higher power we take, the lower value is going to be. If you think about it, the slope of this function is going to look even steeper. So if you have a really high n, let's say if n equals 10 or 5 or something, as omega changes, it's going to look something like this. It's going to jump all of a sudden on the center frequency to 1, because at that point, the value is very close to 1, if not exactly 1. Okay. Even if we take a very high power, it's still going to be close to 1, but the other values, it's relatively smaller. So if you take a high power of it, it's just going to tend to 0. So from this part, we understand that as we cascade a bunch of filters together, it's going to attenuate the necessary frequency a lot better. But sort of as a trade-off, the thing in the middle, it also gets attenuated by a lot. So by actually saying the cutoff frequency, it really isn't like a jump. It really isn't like something like this, right? It's going to happen over time because it's a continuous function. And so there must be a trade-off between attenuating the noise in a system versus getting a larger gain for the desired frequency. Okay, and that's something that you should really take away from this question, apart from getting some exercise with transfer function and stuff. Okay, so that pretty much concludes our walkthrough for question number 2 on the worksheet.